Now, today we want to tackle triple integrals in spherical coordinates. Last time we were doing triple integrals in cylindrical coordinates. And now we are moving to triple integrals in spherical coordinates. Before we can be able to tackle any of the triple integrals in spherical coordinates, we would like to know something about the spherical coordinates themselves. Now, in this case, a point P on any surface of a solid, which is point P here, has got a length. I will be having a length which is rho from the origin. So from the origin up to point P, we are going to give it that length rho, which is written like that. Now, the spherical coordinates of point P should be given by rho theta phi. The theta is normally the angle swept horizontally. The angle swept horizontally, like normally in our polar coordinates, that is the angle theta. So it is swept. So as it can be seen, it can only move from point 0, and the maximum value of theta will be 2 pi. So it moves from 0 to 2 pi. That is, when we are dealing with the full sphere, it will move from 0 to 2 pi. Now, for phi, this angle swept from the z-axis coming downwards, that is offset from the z-axis, we call it angle phi. And this angle phi now, it will be swept from the z-axis, and it can only move from 0 up to a value pi. It can only go from vertical position, from upwards to downwards. So it can only move from 0 to pi. Now, from this analysis, as we have represented here, we would like to know what is the equivalent of x when you are in rectangular coordinates or Cartesian coordinates. What is now equivalent to x? Again, we would like to know what is equivalent to y in terms of rho, theta, and phi. We would also like to give z in terms of rho, theta, and phi. That is, where there is x, what do you input in that place in spherical coordinates? Where there is y and where there is z. We have extracted these two diagrams from this particular condition here. From this particular diagram that we have here, we have just picked Q, P, O, S. And you see there is a right angle here, right angle there. Which you can see that's a right angle. This is also a right angle. So from this one will give us analysis to help us know z in terms of what? Phi. So from this diagram, we can see clearly OQ is our z here. From O to Q is the length z. So z will be equal to, and OQ is an adjacent to this particular triangle. This particular triangle, so adjacent goes with a cosine. So OQ is equal to OP cos phi. OP cos phi, which will just be equal to rho cos phi. Rho cos phi. Rho cos phi. Now we are also interested in O. We are also interested in OS. OS is equal to QP. And QP is the opposite side to this angle phi. And an opposite side will be equal to the hypotenuse multiplied by the sine of that particular angle. So it will be rho sine phi, rho sine phi. So it is rho sine phi. So our QP OS is equal to QP, which will be rho sine phi. Now from this other diagram, we can see clearly OR stand for length, which represents the y coordinate of that particular point. So we say if that represents the y coordinate of that particular point, we say now y, which is equals to OR, will be equal to what? OR, and it is equal to TS. TS is the opposite side to this particular angle theta, opposite side to that particular angle theta. So it will be OS sine theta. But OS before was given as what? Rho sine phi. Now multiplying sine what? Sine theta. So y will be equal to rho sine phi sine theta. X, now x will be equal to x, our s is equal to OT, and OT is equal to what? OT is the adjacent side to this theta, to this angle theta. So it will be OS cos theta, which will just be equal to what? Rho sine phi cos theta, sine phi cos theta. So by doing this, we have been able to convert the rectangular coordinates into spherical coordinates. Therefore, in spherical coordinates, x is equal to rho sine phi cos theta. Y is equals to rho sine phi sine theta. Z is equals to rho cos phi. Now another connection, x squared plus y squared plus z squared will always be equal to rho squared. Now a dv here, the Jacobian of this particular transformation will be rho squared sine phi. Now multiplying d rho, d theta, d phi. So our dv will take that particular format. Now there is, when we are on the surface of a sphere, if we now work on a surface of a sphere, over the surface of a sphere, the length from the origin is not changing. So a small portion on that particular surface will be ds, will be equal to now rho squared sine phi d theta d phi. So when we'll be working on surface integrals, we'll be using this one so much because we'll be working on the surface of a sphere. Spherical coordinates are normally used where the surface is linked to a spherical surface. Now we cannot something small here. 1. For a full sphere, theta will be changing. Theta will be in between 0 degrees and 2 pi. And phi will be changing from 0 degrees to pi. For a hemisphere, above xy plane, centered at the origin, theta will be changing from 0 degrees to 2 pi. Phi will be changing from 0 degrees to pi all over 2. For a first quadrant, of a sphere, theta will be changing from 0 degrees to pi. And phi will be changing from 0 degrees to pi all over 2. For an octant, for a first octant, theta will be changing from 0 degrees to pi all over 2. And phi will be changing from 0 degrees to pi all over 2. That is from 0 to pi all over 2. You say 0, pi all over 2. So this will help us when dealing with the different portions of a sphere. When you need for a full sphere, that's how you use those limits. When you're dealing with the hemisphere above xy plane, these ones. For a first quadrant, we use this. For a first octant, we use those. Now we move to some examples that pertains to analysis of spherical coordinates. So example 1. Determine the spherical coordinates. The spherical coordinates of the point of the point P, negative 1, 1, negative root 2. Negative root 2. So in our solution, x is equals to negative 1, y is equals to 1, and now z is equals to negative root 2. But we know z is equals to, but we know first x squared plus y squared plus z squared is equals to rho squared. This implies what? Rho will be equal to square root of x squared plus y squared plus z squared, which is equal to square root of negative 1 squared plus 1 squared plus negative root 2, which is also squared. So this one will give us, when evaluated, that one gives us an answer 2. So our rho is equal to 2. But we know very well z should be equal to what? Rho cos what? Rho cos phi. This implies our cos phi then will be equal to z all over rho, which is equals to negative root 2 all over 2, which gives us a negative 1 all over root 2. Therefore, phi, which will be equal to, therefore phi here will be equal to cos inverse of negative 1 all over root 2, which will be equal to negative 1 all over root 2. This one, if it is computed, this one gives us 3 all over 4 pi. 3 all over 4 pi. That's the value of our phi. Because we have gotten the value of phi, then our main aim now is to get the value of what? Theta. Rho is there, phi is there, what is remaining is only theta. So, since x is a negative and y is a positive, we can use x to give us the required angle in getting the value of theta. So you say, and from here, since x is a negative, y is a positive, we are in the second quadrant. So we expect our angle to be between pi all over 2 and pi, because we are in the second quadrant. So we say, but x then is equal to rho sine phi cos theta. This implies our cos theta then should be equal to what? X all over rho sine phi, which is equals to our x negative 1, our rho 2, sine multiplying sine phi, and our phi is 3 all over 4 pi, which is equals to negative 1 all over 2 sine 3 pi all over 4 is also equal to 1, it's 1 all over root 2. So this one gives us negative 1 all over root 2. So cos theta is equals to that. This implies what? Our theta is also equal to 3 pi all over 4. 3 pi all over 4. Therefore, the spherical coordinates of point P is given by P into rho 2 theta 3 all over 4 pi phi 3 all over 4 pi. And those are the spherical coordinates of that particular point. We move now to example 2. So determine the Cartesian coordinates of the point P 6 pi all over 3 pi all over 6. Now whatever we have now, these are coordinates which are in spherical coordinates. Now we need to change these spherical coordinates into rectangular coordinates, betterly known as Cartesian coordinates. So in our solution, say, we can see there rho is equals to 6, theta is equals to pi all over 3, and phi is equals to pi all over 6, and phi is equals to pi all over 6. So our x is given by rho sine phi, rho sine phi cos theta, rho sine phi cos 6 sine pi all over 6. Our phi is pi all over 6 cos theta cos pi all over 3, which is equals to 6 times sine pi all over 6 is a half, cos pi all over 3 is also a half, which gives us 3 all over 2. Y will be equal to rho sine phi sine theta, which will be equal to 6 times sine pi all over 6 times sine pi all over 3, which is equal to 6 times a half times root 3 all over 2. Sine pi all over 3 is root 3 all over 2, which this one gives us 3 root 3 all over 2. 3 root 3 all over 2. Therefore, the spherical coordinates, therefore the Cartesian coordinates, the Cartesian coordinates of point P, which is 6 pi all over 3 pi all over 6, is given by P into we have not calculated Z. We have not calculated Z, but we can input here. So that is Our x is 3 all over 2. Our y is 3 root 3 all over 2. And our z is rho cos phi, which is equal to 6 cos phi. And our phi is pi all over 6. Our phi is pi all over 6. That is p into 3 all over 2, 3 root 3 all over 2, 3 root 3, 3 root 3. Okay. So we now move to another example, now dealing with the integrals. We are through with conversion from either Cartesian to spherical, and one also from spherical to Cartesian. Example 3. Evaluate So example 3, we are now evaluating a triple integral. We are evaluating the integral of x squared plus y squared plus z squared dv, but Q here, the solid of integration, where Q is this sphere x squared plus y squared plus z squared is equals to 4. Now, when you get an equation like this, even if you are told or not told, just know it is a sphere. When you have x squared plus y squared plus z squared is equals to a constant. This constant is equal to the radius of that particular sphere when it is squared. So whatever we can see from this is a sphere of radius 2, since 4 is equal to r squared. Therefore, r is equal to what? 2. So this is a sphere of radius 2. After knowing that, we know very well now the length from the origin, which is normally our rho. Rho can only change from 0 to 2 because it is a full sphere of radius what? 2. And we are trying to integrate over the whole solid. So say the integral, now give here, x squared plus y squared plus z squared, this one squared, dv will be equal to a triple integral. X squared plus y squared plus z squared is equal to rho, which is squared. Then we square it. The way it is put here, dv is rho squared sine phi. Then we go for d rho d theta d phi. Now from this, our rho can only change from 0 to 2. And since we are dealing with a full sphere, our theta can change from 0 to 2 pi. And since it is also a full sphere, phi can only change from 0 to pi. 0 to pi. So when we integrate this, We are integrating first with respect to rho. With respect to rho, we are going to get now, with respect to rho, this one will give us rho power 7, all over 7, multiplying sine phi. We put limits from 0 to 2. Then we remain now with the d theta, d phi. When this one is inserted, we are going to get 0 to pi, 0 to 2 pi. 2 power 7, that is 128, all over 7, sine phi. Then we have d theta, d phi, d theta, d phi. Now, when we integrate this one further, with respect to theta, we will have the integral 0 to pi, 128, all over 7, theta, sine phi. And we put limits for theta. And then we remain here with the d phi, which is 0 to pi. When we insert this one here, we'll get 256 pi, all over 7, sine phi, d phi. The lower limit will just bring a 0. When this one is integrated further, we get negative 256 pi, all over 7, cos phi. And then we put limits from 0 to pi, which is equals to negative 256, all over 7, into cos phi is negative 1, minus cos 0 is also 1. So the answer, there is a pi here. There is that pi. So the answer will be equal to 512 pi, all over 7. And that is the answer to that evaluation. So now example 4, we would like to apply triple integral to determine the volume of a solid. So use triple integral to determine the volume of the solid enclosed by the sphere. X squared plus y squared plus z squared is equals to 2z, and the cone z is equals to x squared plus y squared square root. So y squared square root. So in our solution, the spherical coordinates of the sphere is given by of the sphere is given by rho squared being equal to 2 rho cos phi. This implies rho is equal to 2 cos phi. So our rho changes with the position of phi. So since our rho changes with the position of phi, we will be saying our rho is changing from 0 to 2 cos what? Cos phi. Now, when we come to the cone, when we come to the cone, for the cone, Z is equals to root of x squared plus y squared. This implies what? Rho cos phi is equal to root of rho squared sine squared phi cos squared theta plus rho squared sine squared phi sine squared theta, which will just give us rho, sine phi. So this implies what? The equation of this is where cos phi is equal to sine phi. And when this one is solved, gives us that this implies our phi is equals to what? Because we are in the first quadrant, the z value, we are in the first octant, maybe we are on the section above xy plane. So our phi is equals to pi all over 4. Our phi is equals to pi all over 4. When cos phi is equal to sine phi, that can only happen when you are on an xy plane and section above xy plane. The only angle that satisfies that equation is when phi is equal to pi all over 4, because the other one will be below xy plane. That is it. Phi will be equal to pi all over 4. So from here we can now compute the volume. So volume is always given by triple integral. Limits come from the solid concerned. Then we have here dV, which is equal to, so triple integral. So our dV will be phi squared sine phi d rho d theta d phi. Now our rho will be changing from 0 to 2 cos phi. The way we got it here, it will be changing from 0 to 2 cos phi. Now our phi will be dictated by where the cone, the intersection between the cone and any, and that is phi between the cone and the sphere. And our cone now, our phi seems to be changing from 0 to pi all over 4. That is our phi. But theta will be changing from 0, because here we have the theta first. It will be changing from 0 to 2 pi. And phi changing from 0 to pi all over 4. 0 to pi all over 4. So when we evaluate this, we integrate with respect to rho. We get from 0 to pi all over 4, 0 to 2 pi. This will be rho cubed all over 3. Now sine phi Then we put limit 0 to 2 cos phi. 0 to 2 cos phi. 0 to 2 cos phi. Then we remain with the d theta and d phi. When this one is evaluated, we get 0 to pi all over 4. When we insert these limits here, we get what? 2 cubed is 8, so it is 8 all over 3 cos cubed phi sin phi. Sin phi. Then we have d theta and d phi, which will be equal to 0 to pi all over 4, 8 all over 3, theta cos cubed phi sin phi. Because these ones are kept constant because we are integrating with respect to theta. And it's a constant integrated with respect to a variable. You get that constant multiplied by the variable, which is giving us this theta. So we put limits now 0 to 2 pi. Then here we have d phi remaining. When we insert our limits, we get from 0 to pi all over 4. Then 16 pi all over 3 cos cubed phi sin phi d phi. Sin phi d phi. Which will be equal to, when we integrate now with respect to phi, since when you differentiate a cos phi, you get a negative sin phi, then this one we are going to use integration involving polynomial substitution or involving algebraic substitution. So the answer would be minus 16 all over 3 pi cos raised to power 4 phi divided by 4. Then we input now the limits here from 0 to pi all over 4, which is equals to minus 16 all over 3 pi into when we input this, when we input pi all over 4 here, cos pi all over 4 is 1 over root 2. When it is raised to power 4, we get a quarter. A quarter divided by 4 is 1 over 16 minus now a quarter. Minus cos 0 is 1. 1 power 4 is 1 minus a quarter. Minus a quarter. Yes. So this one will be minus 16 all over 3 pi into that's 1 over 16 minus 4 over 16. So minus 3 goes with that, 16 goes with that. So which is equals to pi cubic units. That one will be equal to pi cubic units. And that's the volume of the said solid. So in our example 5, we say evaluate from -1 to 1. Negative root of 1 minus x squared to root of 1 minus x squared. 0 to root of 1 minus x squared minus y squared. X squared plus y squared dv. So in our solution, as we can see, these are values of z. So this is for z values, it is enclosed. It is enclosed from, we can say this is from -1 to 1. From minus root of 1 minus x squared to 1 minus x squared positive square root. From 0 to root of 1 minus x squared minus y squared. X squared plus y squared. Now dz, dy, dx. Dz, dy, dx. Now, these are z values. So it is from z is equal to 0 to z is equal to positive root of this. And this is an equation of a sphere. So it is the portion of the sphere above xy plane. Now, these last two integrals will indicate the nature of the portion of that sphere above xy plane. Since these last two limits denotes that we are taking these limits from a circle of radius 1, so it is a full circle. If it is a full circle, then it seems that the solid we are working on is a hemisphere above xy plane. So if it is a hemisphere above xy plane, we can now convert this into spherical coordinates. And then say this is the integral from x squared plus y squared becomes what? In spherical coordinates, it will be rho squared rho squared sine squared phi cos squared theta plus rho squared sine squared phi sine squared theta. Sine squared theta. The whole thing now. Now multiplying dz, dy, dx, which will be rho squared sine phi d rho d theta d phi d rho d phi. Now our rho is changing. This is a sphere of radius 1, 0 to 1. Theta is changing from 0 to 2 pi for a hemisphere above xy plane. And phi is changing from 0 to pi all over 2. Phi is changing from 0 to pi all over 2. When we simplify this, we get 0 to 2 pi all over 2. 0 to 2 pi, 0 to 1. And now this plus this will simplify to rho squared sine squared phi. And we have another rho squared here sine phi. So multiplied together, we will get now rho power 4 sine cubed phi d rho d theta d phi, d rho d theta d phi. When we integrate that, What do we get? Integrate that. We get 0 to pi all over 2, 0 to 2 pi. Then we get rho power 5 all over 5 sine cubed phi d theta d phi. And here we put limit 0 to 1 to 1. Put limit 0 to 1, which will just be equal to 1 all over 5 will come out. We have 0 to pi all over 2, 0 to 2 pi. Then we have sine cubed phi d theta d phi, which will be equal to 1 all over 5, 0 to pi all over 2, sine cubed d theta. We are integrating first with respect to theta. So we'll get theta sine cubed phi. Now we put limits from 0 to 2 pi. 0 to 2 pi. Then here we have d phi, which will be equal to 1 all over 5, 1 all over 5, 0 to pi all over 2. Then we have 2 pi sine cubed phi, sine cubed phi d phi. Two pi, we take it out, it will be 2 all over 5 pi. Now we are integrating. We are now integrating sine cubed with respect to phi. Then we'll now split sine cubed first so that we can be able to integrate. So sine cubed can be written as cos. Sine cubed can be written as sine squared phi multiplying sine phi d phi. So which will be equal to 2 all over 5 pi. The integral from 0 to pi all over 2. This one now we have it as 1 minus cos. Sine squared phi is the same as 1 minus cos squared phi. Now this one multiplying sine phi d phi, which will be equal to 2 all over 5 pi. The integral from 0 to pi all over 2. One term sine phi is sine phi minus cos squared phi sine phi, the whole of this d phi, which will be equal to 2 all over 5 pi. 2 all over 5 pi. The integral of sine phi is minus cos phi. The integral of this will be plus a third cos cubed phi. The integral of cos squared phi sine phi will be plus a third cos cubed phi. And then we put limits from 0 to pi all over 2. From 0 to pi all over 2, which will be equal to 2 all over 5 pi into 2. Cos pi all over 2 is 0. Cos pi all over 2 is also a 0. So we get that one as 0. So 0 plus 0 plus 1 minus minus cos 0, cos cubed, cos cubed, cos 0 cubed is just 1, 1 cubed just 1, so minus a third. So the answer here is 2 all over 5 pi multiplying 2 all over 3. So the answer is 4 pi all over 15. 4 pi all over 15. So that will be the end of analysis of triple integrals in spherical coordinates. When we meet next time, we'll be seeing how to have change of variables in double integrals and change of variables in triple integrals, which will lead us to analysis of Jacobian of a transformation, as we have some regions or solids which should be transformed first before we carry out our multiple integration.